make my presentation as lucid as possible, but I don't know, because giving a public lecture and I mean students like you, it is always difficult. Okay? If you have any query, you can always ask me. There is no problem. As much as possible, I will of course answer your questions. Okay. So the gamma ray view of the universe. All of you must be knowing, because your teachers told me that you are all in 11th standard now. So what is gamma ray? Okay. This gamma ray actually, I mean, it all started with radioactivity. I mean, when the radioactivity was discovered, it was around 1896 or so. Since then, we have the idea of this gamma ray, alpha ray, beta ray and all. Okay. Now, we want to study the universe in this gamma rays. Now, the gamma rays are not necessarily to be produced in radioactivity. Okay. Gamma rays can be produced in some other way also, and our cosmic sources, they are regularly producing gamma rays, and those gamma rays are of very high energy. Okay. You people must be aware of the energy unit 1 electron volt already. From 1 electron volt, then if we multiply it by 1000, this is 1000 electron volt, which is 1 kilo electron volt. Okay. Similarly, we can define 1 mega electron volt, which is 10 to the 6 electron volt, giga electron volt, which is 10 to the 9 electron volt, and tera electron volt, which is 10 to the 12 electron volt. It's a huge energy. And those photons are really produced in our astrophysical sources. But the question is that why should we observe those sources in gamma rays? What is the necessity? Because our, and this is our electromagnetic spectrum, it extends from radio wave to gamma rays, and radio wave has the longest wavelength and gamma rays have the shortest wavelength. Now, astronomy is the ancient science, okay, I mean branch of science, and we always do, I mean we are acquainted with this optical astronomy. If we see, the night sky, this photograph of galactic arm was taken by my colleague Sagar Godambe in Arizona. So, if you see, you just see it's a lot of light from distant stars, galaxies, gases and all. But through naked eye, which is sensitive to the visible light, we actually cannot do much. If we want to know things in detail, then we should have a telescope. With a telescope, what we can do, we can pinpoint a particular object and study that object in detail. Here I have just shown Saturn, a planet, that is SN 1987A, which is a supernova remnant. Okay. This was seen by our observers when it exploded from the Earth. And there's a ring around that supernova remnant. There are two stars in the field of view. I mean, we don't know exactly whether it's the stars or galaxies. For that, we need to have a proper study. Then we have a stellar cluster, that is cluster of stars. Then the Orion Nebula, that is a place where star formation is going on even now. And the galaxy cluster, that is this is actually a Hubble image where lots of galaxies are seen and they have a coherence in their motion and everything. Okay. There is another way to look into an astrophysical object, that is a multi-wavelength study. The same object you see in different wavelength range. For example, here I am showing the Crab Nebula. It is again a supernova remnant. Why I am talking about supernova remnant again and again, it will be clear in next few slides. So the same object, when it is in radio, infrared, optical and X-ray, they look very different. That means that all these radiation which is coming from this source, they are not emitted homogeneously from the whole object. X-ray is coming from some region, optical is coming from some region, radio is coming from some region, similarly infrared. So if we want to have a holistic view of this object, we should look into this object with different wavelengths. And when we merge all together, we get a picture like this, where it is said, here you will have to trust me because I cannot explain all those things here, that there is the supernova remnant, there is a pulsar sitting inside, and the pulsar is throwing some matter out, which is interacting with the surrounding mass and giving all these radiations and everything. Okay? So this is the way things were going on. We went up to X-ray. Now the question is, why we will go for gamma rays? Now this gamma ray astronomy is very much connected to the discovery of cosmic rays. So we'll have to go back to around 1900, when you people have studied gold leaf electroscope in your studies. Scientists used gold leaf electroscope. So if you charge the gold leaf electroscope, you will see that the gold lips, they repel each other and there's a gap is produced. What happened? They used to leave this gold leaf electroscope in a very, in a proper manner, in a very insulated environment. Still they used to find that the gold leaf electroscope is discharging. So, means the gap of those gold lips are decreasing slowly with time. The question is why? Gold leaf electroscope is discharging means some charge is coming and neutralizing the existing charge. So from where the charge is coming? Okay? And that was a question troubling scientists very much. Some people said, okay, say 1900, that time the radioactivity was already discovered. Some people said, okay, the radioactivity in the environment or in the earth is causing the problem. But where is the radioactivity? People are not getting them actually. Then it was in 1912, Victor Hess, this is Victor Hess, he carried out one balloon experiment. His argument is that, let me carry a few electroscopes. This is the electroscope there are 6 such electroscopes he carried, and this is now kept in Washington DC National Archive. He's an Austrian physicist. He carried 6 such electroscopes on a balloon, and he himself went up to a 5,300 meter without oxygen. Okay. He found that as he is going up in altitude, the ionization is increasing. That means the ions produced, available there in number is much more. This is a later experiment done by some other scientist, where he went up to 8,000 kilometer or more, 8 kilometer or more in altitude. So he found that the ionizing radiation must be of extraterrestrial origin. It is not coming from the earth. Had it come from the earth, the intensity should reduce and this ionization should reduce. Okay? So ionization increasing means the radiation is of extraterrestrial origin. Then people ask question, is it the sun? The answer was no, because they carried out the observation in night and also during the eclipse. So it is not the sun, the result is the same. So it must be of some extraterrestrial origin. And then Millikan. Have you heard of Millikan, who did that oil drop experiment? Millikan called it cosmic rays. That's how the name came. So a lot of radiation with extraterrestrial origin are coming and they're bombarded on us. Then the question is, what is the origin of such radiation? From where these charged particles are coming? So to understand that, they started many experiments, and in those days experiments were primarily carried out on balloons. You have to go to higher altitude, but because there was no satellite, so balloon experiments were done. And later on in 1950, when the first satellite was launched, after that a lot of experiments were carried out in satellite based instruments. They found that this cosmic ray is primarily consisted of 98% protons and nuclei, okay, and 2% electrons. Protons, fine. Nuclei, it is helium, nickel, iron, all those. The abundance is just like the abundance what is found in sun that was there, and except for some low atomic number elements. So whenever I will talk about cosmic ray now onwards, it is primarily the proton I will talk about, okay? Because among this, it is almost 90%, I mean, among the proton and nuclei, 90% are protons, 10% are the remaining other nuclei. Okay, so the question is, how protons are accelerated to high energies? Now, what is the energy? What is the maximum energy available? For that, we need to study the cosmic spectrum. All of you know what is spectrum? You have studied this kind of thing. There's a dispersion phenomenon where when the white light falls on a prism, it's split into this Vigyan. Now, if we have an experiment where I have detectors for each wavelength, separate detectors, and I measure what is the intensity falling on it, and if I plot here the wavelength and the intensity, what we get is a spectrum. So this is in case of light. What will happen for particles? In case of particle, what we do, we take certain energy bands, that is 1 MeV to 2 MeV, 2 MeV to 3 MeV, and find out how many particles are there in each bin. So what we get is a spectrum. Here the spectrum looks like this. It is a straight line, almost a straight line. Actually, this is plotted in log scale. Since you are already in 11th, you must have studied log. So here the log of energy, and here it is the log of number of particles, and that is a straight line. So that means if you go back to the actual number, it will come something like, and it has a negative slope, so it will come like number will be proportional to the energy to the minus some constant. Okay, this we call a power law. The power law is a non-thermal distribution. What do I mean with respect to this? When you study the gases, we know the gas molecules, they follow Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution can be specified if you specify just the temperature of the gas. So a single temperature can describe the complete distribution of the particles. But here we cannot do that. We cannot reproduce mathematically this curve using a single temperature. So it is not a thermal spectrum. So what we see here is a non-thermal spectrum. So cosmic ray gives us the information about the non-thermal universe. And non-thermal universe is a part of the, all the phenomena in the universe where equilibrium is not attained, because something in equilibrium can be very well described by a single temperature. Okay. Now you see the slope here in this plot from this to this and this to this, they are a bit different. And that that energy is called the it is 10 to the 15 electron volt, and this energy is known as the knee energy, because one can show that this shape can be just like a human leg, where this is a bend, where it's a knee like bend here, and there is an ankle here. Actually the slope is changing here again. So that's the description of this, the shape of the spectrum. Now what is important here is that see the maximum energy, which is 10 to the 20 electron volt. Okay, you people must have heard about the LHC, Large Hadron Collider. Have you heard? What is the maximum energy it produces? For protons, do you know? It is 7 TeV, that means 7 into 10 to the 12 electron volt. And it's a huge state-of-the-art technology. You know that the collider circumference is 27 kilometer. It crosses France to Switzerland. Okay, so it's a huge thing, and that produces 7 into 10 to the 12 electron volt. But nature is producing 10 to the 20 electron volt. The question is how? And along with that question, the how, and the where and how they are produced, that also matters. Okay? So we are in search of origin of cosmic rays. Now we can have a guesswork. I showed you that 10 to the 15 electron volt here is the knee is here, knee of that means the slope is changing. Now this 10 to the 15 electron volt has a significance. Actually, all those particles which are having energy less than 10 to the 16 electron volt. Okay, let me tell you one thing. This is our galaxy. Okay, the structure in schematic diagram. This is the structure of our galaxy. This is called the galactic bulge. This is the galactic plane, and this is in this galaxy we have a lot of magnetic field, and that magnetic field is random magnetic field. Okay, the strength of the magnetic field is of the in microgauss. But what happens when a charged particle enters a magnetic field? It gets deflected. Okay, so what will be the trajectory of a charged particle in random magnetic field? It will be like zigzag and random, but the radius of that actually if there is a magnetic field in this direction and the particle enters, it has a gyrating motion. So the radius of gyration, it will depend on the energy of the particle. So more the energy, larger the radius. So for particles which are having energy less than 10 to the 16, their gyro radius is such that it is less than the thickness of this galactic plane. Okay, whereas for energies greater than this, greater than equal to this, the gyro radius will be much more. So all those particles which are having energy greater than 10 to the 16 cannot be confined within our galaxy. So if it is so, then they cannot be actually accelerated in our the high energy particles cannot be accelerated in our galaxy. So they are possibly of extragalactic origin, whereas all particles less than 10 to the 16 or say up to 10 to the 15 electron volt, they are possibly originated in our galaxy. So where it is? It was Zwicky, Fritz Zwicky in 1933 in Caltech. He proposed that they are possibly accelerated in supernova remnants. Why? Because the supernova remnants, they have huge energy available with them. What is supernova remnant? When a massive star, say 10, 15 solar mass star, it exhausts its fuel, at that time, the core of the star, which is primarily made of iron, it collapses into a neutron star, and the remaining part of the star, it bounces back from the neutron star and moves with a very high velocity. How high? It is more than sound speed. It is nearly 10,000 kilometers per second, such kind of speed it moves in the interstellar space. And it creates a shock. Okay, this is supernova 1006. It is just like when we know that the aircraft, it crosses the sound speed, it creates a shock here, okay, which you call the sonic boom. Similar thing happens in this interstellar medium. And Fermi proposed a mechanism which can tell us how these particles can be accelerated in such shock. Now, supernova, and later on people did a lot of calculations and they found that the maximum attainable energy by the particles in supernova shock can be 10 to the 15 to 10 to the 16 electron volt. Okay, so this is all theoretical predictions, but there is a problem. Problem is the following. Suppose there is a supernova remnant here and a proton which is accelerated in this cosmic ray, accelerated here, comes out of the source of the supernova remnant. It's a charged particle and you have interstellar magnetic field. So its actual direction will be lost. What will happen? This will gyrate here and there and zigzag motion. Finally it will reach the Earth. And Earth, we will think that it is probably coming from here in this direction. So a charged particle cannot reach the Earth directly from the source. So just by receiving a charged particle here, we cannot say from where they are coming. On the other hand, if there is a neutral particle, so photon or neutrino, if they are emitted from this, they will be unaffected by, the motion will be unaffected by this interstellar magnetic field. So it can directly reach us. So the point is, when we are talking about this gamma ray or neutrino, what is its relation with the cosmic ray? Yes, there is a relation. Relation is the following. If the energetic charged particles are there in some astrophysical object, it can interact with its ambient medium and give radiation. And we can pick up that radiation. So what are the radiation? If there are energetic electrons, these energetic electrons can interact with the magnetic field and give a photon, gamma photon or X-ray photon, which is through, and the process is called the synchrotron radiation. It can also interact with a low energy photon, because low energy photons are available in stars very much. So what will happen? There is a low energy photon and there is a high energy electron. If they collide, then the high energy electron will dump energy to the photon, and the photon will become a high energy gamma ray. Also, if there are energetic protons, then a proton can interact with the matter in the star and give rise to neutral pions, which can give rise to gamma rays. It can also interact with the photon to give rise to pions, and which can give gamma rays. There are some other interactions also, that proton can interact with the photon and give other pions and charged particles. Okay. So the theoretical prediction is that if there are energetic particles in some astrophysical source where they are produced, then they can produce gamma rays. So if they can produce gamma rays, those gamma rays will straight reach us. If we can detect them, then we can talk about the origin of cosmic rays. Okay? So now we will have to detect gamma rays. How will you detect? We need some detector. When we talked about the optical astronomy and all, we have telescope. Now each telescope is connected with CCD camera, so we can take the image and all. Now, so here we will talk about gamma ray telescope. These telescopes are not like optical telescopes. So how they look like? Before going to that, let us see the atmospheric transmission. Our atmosphere actually does not allow any radiation to pass through, and because of that we are saved. If a TeV photon reaches the earth directly and it hits us, of course we would get cancer straight. So what happens is that our atmosphere is opaque to gamma rays, X-rays, here UV also, some part of IR. Only this visible light and some part of radio can reach us. So when gamma rays cannot penetrate the atmosphere, Earth's atmosphere, how can we detect them? There are two ways. One is that we send a satellite with detector above our atmosphere and directly detect the gamma rays. Okay? This is the Fermi satellite sent by NASA, which is presently in orbit. It is giving a lot of useful data. It was launched in 2008. It detects gamma rays from 10 MeV to 100 GeV. Okay. Now, if we look at this cosmic ray spectrum again, what we see, what is important here, the number of particles in this spectrum which are given here. This is one particle at the top. It is, this is not working. At the top it is 1 particle per meter square per second. And if you see the rate at the below, at a very high energy, it is 1 particle per kilometer square per year. Okay? So if we want to, if we think that these particles are responsible for the gamma ray emission, then our gamma ray rate will also be like this. So at a low energy, if we go, so 1 particle per meter square per second, this is fine. So if we send a satellite of 1 square meter area, detector on a satellite with 1 square meter area and observe it for 60 seconds, we expect that 60 gamma rays it will detect. But what will happen if we send such a detector to see something in TV? We will hardly get any photon. So to detect a sufficient number of TeV photons, we need a huge collection area, and that huge collection area detector cannot be launched on a satellite. So we will have to do something else. Okay? Now here I just showed how this Fermi detector works. This is something electron-positron generator. This incoming gamma rays produce electron and positrons here, and their energy of those particles are measured. There are two types of detectors. One is a large area telescope and another is a gamma ray burst monitor. They are on board Fermi satellite. Okay. Now the ground-based telescopes. This is called the Cherenkov telescope. These Cherenkov telescopes are used to observe sources in gamma rays. You can see the size of these telescopes. This is a Magic 1 and Magic 2. These telescopes are actually put in La Palma, Spain, but primarily this is run by the German groups. Now, how these telescopes work? What happens when a gamma ray enters the Earth atmosphere? When a gamma ray enters the Earth atmosphere, it interacts with the nucleus of these atmospheric these elements, I mean nitrogen, oxygen and all, and it produces electron and positron. Those electrons and positrons, they further interact, produce gamma photons. Those gamma photons again produce electron-positron pair, and finally, and same thing happens in case of a cosmic ray also, and finally what they do, they produce a lot of Cherenkov radiation. Okay? This is called extensive air shower, and I don't know whether you are aware of it. The idea of extensive air shower, the first, it was given by Homi Bhabha. And a lot of work was done in Calcutta also by Professor D.M. Bose and Bibha Chaudhuri. And that is during the Second World War time. Okay. Now, so what happens? Now, these cosmic rays or these gamma photons, when they enter atmosphere, they produce a huge amount of electrons and positrons in the atmosphere, and which produce Cherenkov radiation. Do you know what is Cherenkov radiation? Do you know? See, what happens when a charged particle moves through a medium with a speed more than the speed of light in the medium. Just note it carefully that more than the speed of light in the medium, because Einstein says that nothing can move with a speed more than the speed of light, but that is the speed of light in vacuum. In a medium, the speed of light will be decided by the refractive index. Okay? So the speed of light in that medium, if it is, whatever it is, if the charged particle moves faster than that, then the medium emits a radiation which is called the Cherenkov radiation. Okay, so a lot of Cherenkov radiation is produced, and what we get is something like this. We get a cone. There is a pool of Cherenkov photons which are coming and falling on at the ground with an angle of 1 degree here, and this is say around 7-8 kilometers from the sea level. So a gamma photon enters the atmosphere, produces this particle shower, and these particles produce the electrons and positrons in this shower, they produce the Cherenkov radiation. So if we can collect this Cherenkov radiation, then we can get some information about the shower which is producing it. Okay? So, okay, the number of Cherenkov photons which are produced here for a single 1 TeV photon is around 10 to the 6. So 10 to the 6 Cherenkov photons are present in a region with a circular region with a radius of 120 meter. Okay? So if we can collect this, so that is what we do in Cherenkov telescope. So this telescope, it can collect this Cherenkov photons, and an image will be so this is the telescope, and this is the telescope, and here there is a camera. If you go back to that, so here this is the basket of the telescope, what we can see face on, and these are the mirrors in the basket, and those mirrors reflect the Cherenkov photons, and there is a camera here which is made of photomultiplier tubes, and those photons are then produces a signal in those photomultiplier tubes, and we collect that signal. So what we get at the camera is an image like this. This is the image produced by the Cherenkov photons. Okay, and what is this? What is this image actually? This is the image of that portion of the shower which is producing the Cherenkov photons. Because the image of an object what we get is that portion from where the light is coming. Okay, so we get this. Now the question is, any shower, be it a gamma ray, initiated by gamma ray or a proton, can produce this kind of image. So how will you differentiate them? See here, this is the first one is the gamma ray initiated, image of a gamma ray initiated shower, which has a very well defined shape, whereas that one is a proton initiated shower which has a very distorted shape. So from this we can identify that how many gamma photon initiated showers we are actually getting. Okay, and then there are a lot of analysis tools are there which we use to finally extract the gamma ray signal. Here, this is our Indian telescope at Mount Abu. This is a tactic telescope which is at an altitude of 4,500 feet. This is run by BARC, and this is the Hagar telescope run by TIFR, Tata Institute of Fundamental Research, at Hanle at 14,500 feet altitude. Okay, this telescope, tactic telescope, is an imaging telescope, but this is not an imaging telescope. They use some other method or the wavefront sampling method. So here we have the other telescopes which are operating in the world. This is HESS telescope in Namibia. This is again run by a German group, but it's a huge collaboration. This is MAGIC, I have already shown, and this is the Veritas telescope at Arizona. Okay. The question is that did you really see anything in gamma rays? I'm talking so much. Is there any output actually? This is the sky observed by the Fermi satellite telescope. What you see here, this bright region, this is actually the galactic plane. Okay, and this color actually represents the intensity of the gamma rays what we have received from the sources here. And there are dots you can see at these places. These are the point sources. They are actually there can be supernova, there can be pulsars, there can be galaxies which are emitting gamma rays. Okay. Now here again the same thing. These are the sources. These are the supernova remnants which are seen by Fermi Space Telescope. And as I mentioned that this is in the energy range of 100 MeV to 300 GeV. So these are the different sources. Fermi has so far seen nearly 5,000 sources which are emitting gamma rays. Out of them, we still don't know the nature of 1000, this unassociated source, which is, the number is 1834. Otherwise, we have seen 224 pulsars, 38 supernova remnants. There are many galaxies we have seen. So so this telescope tells us that yes, so many sources are actually emitting gamma rays. So there is a possibility that these sources are the actual source of cosmic rays. Now, what is the status with the ground-based telescopes? Ground-based telescopes have seen so far 225 sources. They are supernova, pulsars, and blazars primarily. This is the kind of distribution we have for these sources. Now, let me tell you that the puzzle is still not actually resolved. These are different supernova remnants observed in gamma rays. Okay. Now, one thing I should mention here, that in optical or X-ray or even in UV, we can generate an image. I mean, just taking a photograph. Similarly, we can take an image of an astrophysical object in these wave bands. But in gamma ray, imaging is not possible because focusing gamma ray is very difficult. I mean, till now it is not possible. So we cannot take the photograph of an object in gamma rays. But what I am showing you here, we call it a sky map that is generated by doing some analysis, following some analysis procedure, where we can see that from which region in the sky the gamma rays are coming. Okay, so and then they are compared with this. You can see these green contours. These green contours are the contours which are observed in radio. So whether we are looking at the source really or not, that is actually confirmed by these contours. And secondly, we can also say whether the gamma rays are coming from the same region from where the radio is coming. Okay, so these are the sources, different supernova remnants. Here, few more, and you can see this emission, see RxJ1713.7. This is this arc. This is actually the shock region from where the particles are accelerated and the radiation is coming. This is another interesting source. This is SN1006, which is seen in gamma rays. Now, if you see the image in X-ray, it is exactly the same region from where the gamma ray and X-ray are coming. That means this is the region probably where these particles are actually accelerated. But as I told you that we study spectrum. Similarly, here also we study spectrum. I am not going into the details of it, but the problem is that when we study theoretically this spectrum, we can actually reproduce, theoretically we can reproduce this spectrum from using just electrons. That is a process like synchrotron comptonization, what I showed you initially, or with protons. So anything will work. Electrons will also work, protons will also work. So the question is that, the question what we were asking, that radiation is produced by protons, that is a cosmic ray, primarily, that question is still not answered. We cannot say that yes, this spectrum from supernova remnant can be explained only using protons, not by electrons. Until and unless we can say that, we cannot say that yes, this supernova is a cosmic accelerator. Okay, so the situation is at this moment is like that. Now this is your in the galactic plane, when we look in the TV energies, we see there are so many sources that are actually giving gamma rays, I mean TV gamma rays. Okay? This pulsars, for the moment I just skip. Now, I'll come there.
So by 11 or 11?
Finish it. So now we come to something very interesting called active galaxy. What is an active galaxy? We know the galaxy, I mean our galaxy, the Milky Way. Do you have any idea that how many stars are, sun-like stars are there in our galaxy? Any idea? Okay, 10 to the 11 stars, you can see, I know. and each star has a luminosity 10 to the 33 arcs per second. So the total luminosity of our galaxy is 10 to the 44 arcs per second. Okay? But this is an active galaxy. What is that? For this particular galaxy, this is MRK 421, the center of the galaxy is very bright. The luminosity of the center of the galaxy itself goes from 10 to the 46 to 10 to the 48 arcs. That means few orders of magnitude more than the Milky Way kind of galaxy. Okay? This kind of galaxy for which the center of the nucleus of the galaxy is very bright is called active galaxy. And there are active galaxies like this. These are the jets. Actually, this is the center of the galaxy from where the matter comes out with a very high speed. And this speed is measured. It is almost the speed of light. Okay? These galaxies are all very bright in radio wavelength. So, the schematic of this active galaxy is something like this. All these activities and this high luminosity, people say that some supermassive black hole whose mass is 10 to the power 9 solar mass is responsible for this kind of unusual activity for this galaxy. And at the center, the black hole is sitting, it is pulling matter from all around. So there is a disk of, formed by that matter which is coming and falling on the black hole. And black hole throws out some matter. How it is thrown out, we don't know. There are some process, people say, but they are just ad hoc. So, and that matter comes out with the speed of, almost with the speed of light. This is called a jet. And these jets actually can have shocks again, and those shocks can accelerate particles and give rise to gamma rays. Now, out of these active galaxies which are having jet, there is a certain class of galaxies for which the jet is directly directed towards the Earth. So when we look at those galaxies, we actually look into the jet straight. So such galaxies are called blazars. And these blazars are strong emitters of gamma rays. So again, using gamma ray telescopes, we study these blazars and we try to find out what is the possible emission mechanisms. Okay, again there is a problem. This is a Blazar spectrum which can be explained by introducing the electrons. So the question comes, where are the protons? So what we need a better telescope. We need better telescope to work on, and we will have to measure the photons up to 100 TeV to pinpoint the source of protons. Okay, because one can show that electrons cannot produce 100 TeV gamma rays at all. So, upcoming telescope. This is a telescope which is coming up in Hanle, India. We are, from BIRC, TIFR, Saha Institute, Kolkata, and Indian Institute of Astrophysics, Bangalore. We are constructing this telescope at Hanle. You can see in the backdrop this TIFR present telescope. This telescope will see the first light next month, if this observation is possible, because it is at a 14,500 feet. The temperature is already going to -20 at night. Okay, so this telescope is ready. This will operate in the energy range of 20 GeV to 20 TeV energy range. You can see the structure. Here there is a truck standing. Actually, the camera is at a height of 45 meters from the base. It's a huge telescope. The dish is 21 meter. The basket, 21 meter diameter. This is it has not fallen down on the ground. It is the parking of the telescope. Okay, telescope will be parked in this fashion. Now there is another huge project is coming up. This is called the Cherenkov telescope array. Here there will be two, one in the northern hemisphere and another in the southern hemisphere. Northern hemisphere array will be in La Palma, Spain, and the southern array will be in Paranol, Chile. This array will consist of three types of telescope. One is a small size, one is a medium size, and is a large size telescope. And it will have an energy range from 20 GeV to 300 TeV. Okay. So India is a part of this collaboration. These are the collaborating countries. More than 1,500 scientists are working, 200 institutes and 31 countries. So these black patches, these are the collaborating countries. Okay. So we are also part of this collaboration. So you people can pursue your studies in basic science and do this kind of things, exciting things. This telescope will be operational in 2024, or 25. It will the first phase will start. These are the telescopes already made for this particular CTA project. One telescope is made. This is a small size, this is a large, and this is the third one is the medium sized telescope. These are all Cherenkov telescopes. So the important aspects for these new telescopes is that here one can study the pevatrons, that is the sources which can accelerate particles up to 10 to the 15 electron volt. And if we can really detect, because this has the potential, these telescopes have the potential to detect 100 TeV gamma rays. Okay, it can study something called the extragalactic background light by observing distant blazars, and also it can study the dark matter. So study of pevatron, again the Crab nebula. So 100 TeV photon will ensure that 10 to the 15 electron volt protons are there in the supernova remnants. So it is very much expected that they will detect it. How will the study of extragalactic background light will be done? See, when gamma rays come from the extragalactic sources from a large distance, then it interacts with the intergalactic photon background and it produces gamma rays. Electron and positron pair. So the number of gamma rays which are coming will reduce, and one can study that change in the spectrum, which will give rise to give the information about the EBL. So I will conclude. Even after 100 years of its discovery, cosmic ray is still a puzzle. It is possibly waiting for you people, to solve it, solve the puzzle. Okay? Secondly, these new telescopes will possibly give informations about these cosmic accelerators, determination of EBL, because determination of EBL will have consequence on the origin of the universe and the nature of dark matter. So finally, for you people, study basic science in future, stretch your imagination, and be a part of many exciting results, because lot of data will come. We will have to analyze them to get the results, to understand the nature. Thank you. So any question?
Dark matter can emit gamma ray?
No. Dark matter, through some channel like annihilation of dark matter or the decay of dark matter, there are many, can produce gamma rays. Can produce gamma rays. Okay, see, there is a model of the weakly interacting massive particles, WIMP. The WIMP can decay and can give rise to gamma rays through different channels. Massive particles. Showers. Yeah. Actually, I could not tell this to this audience. Shall I go back? See, the first interaction is a nuclear interaction. Okay? It will create pions. And nuclear interaction has a large transverse momentum. Okay? So because of that, it will spread. And next is that those pions will create electrons and positrons, muons. So they will initiate electromagnetic showers. So there will be many mini showers over a larger space. Yes.
Thank you, sir.
Thank you.
It's quite informative for them.
Okay.
Just 11